Hey everybody, we're continuing chapter 12. Got some reactions to talk about for alkenes that we started talking about last time, and right now we're on number 3, which is reaction electrophilic addition of halogen acids like HBr, HCl, HI, and we call these Markovnikov. I don't know if you remember that. What does Markovnikov mean? Markovnikov meant that if you have an alkene, and these are all alkene reactions, that the HBr would add to the the halogen part, the Br, chlorine or iodine, would add to the more substituted side of the alkene. That's what Markovnikov meant. More substituted, alright? So here's an example of, just a simple example, cyclohexene, some HX type thing. Alkene attacks the HX, makes a carbocation, X minus attacks, and you get the product, alright? Another example specifically with HBr, and these are the same molecule, so sometimes we don't draw the H, right? Okay, and this actually shows the Markovnikov business of how the Br goes to the more substituted side. Why does the Br go to the more substituted side? Because it's a more stable carbocation, right? So primary carbocation never forms, so that wouldn't make sense that you get a primary product. And that's why we call it Markovnikov. So a couple more simple examples of Markovnikov addition of the halogen acid would be HI. Alright, what do you think is going to happen? We're going to add hydrogen to one atom of the alkene, iodine to the other. Is the iodine going to go to the more substituted or less substituted? It's going to go to the more substituted. Okay, and I'm drawing the H, but you don't have to draw the H. This is understood. These are the same molecule, right? Those are the same molecule. Okay. How about if I have this molecule and I use HBr, we assume excess, so like a bunch of HBr. Now we have two alkenes, and you can envision that one Br goes there, one Br goes there. Okay, and I'm ignoring the H's. Of course, they're being added, but we're not going to worry about that. Drawing that. Okay, just as a little preview, there is an anti-Markovnikov version of this, because this is Markovnikov's rule, right? The iodine or bromine goes to the more substituted side. There will be an anti-Markovnikov version, and that's later in the chapter. I think near the end of the chapter. Which is going to be, if you do the same exact thing, but we use like HBr and peroxides. We'll define what peroxides are later. It's just an organic molecule. In this case, you actually get the Br on the least substituted side. So it's not going to be a carbocation type mechanism. These are all carbocation mechanisms. This will be different, alright? Different mechanism. So we'll see that later. I'll give you a hint, it's a radical mechanism. This one's going to be a radical mechanism. Cool, a really cool mechanism actually. So we'll see that later. Okay, so back to the normal reaction, the carbocation one. Since it is carbocation, you could imagine that there might be a radical carbocation rearrangement possibility, and yeah, you could actually envision something like this happening, kind of weird. So the H gets attached to the end, and then it hydride shifts to make a tertiary carbocation, right? So yeah, this happens. And then that gives you a secondary carbocation, and a hydrogen right there, and then a hydride shifts. I'll let you draw that part, and I'll also ignore the hydrogen because we don't have to draw the hydrogen every time. And then Br minus attacks. So you can fill in the mechanism, but that's a H shift, right? Hydride shift. So when you have carbocations, you can do carbocation rearrangements. Alright, so next reaction. We can convert alkenes to alcohols. There's going to be a couple ways to do this. This is going to be the bad way, and we'll show the good way actually in a little bit. So keep it. We introduced the bad way, and then we'll show the really good ways. So this bad way would be using a non-nucleophilic acid, and water. Non-nucleophilic acid and water. It's another carbocation mechanism. It's actually really easy. This is Markovnikov. It's a Markovnikov reaction. So if we do an alkene and we react with H2SO4 and water, so non-nucleophilic acid and water, you get an alcohol. Alright, the mechanism is super easy. Alkene attacks the acid. So acid is just something that can be attacked, and that gives you a carbocation. Again, the carbocation would go to the more substituted side. Alright, and then you can kind of see where we're going now. How do we get to the next step? Just water attacks it. Okay. OH2 plus. How do we get to the final product? We just lose a proton. So minus H plus, something takes it off, maybe another water or something. OH2 gives you the alcohol. Alright? Why are we calling this the bad way? Because through carbocations you can imagine carbocation rearrangements, right? So the good ways are going to avoid carbocation rearrangements. So we'll talk about the good ways in a second. Okay, number 5. Electrophilic. So all these reactions are electrophilic. So we're attacking electrophiles with an alkene. Electrophilic addition of halogens to alkenes. What's a halogen? Like Br2, Cl2, etc. Alright, so another pretty simple one. The trick here, what do you think is being added? Like what is being added? Br2, Cl2. Maybe both of those elements. It could be Br2, it could be Cl2. Those are the typical ones that we see. And this is, of course, different from the other reaction you learned of Br2. What's the other reaction you learned of with Br2? Think way back. Like if we had an alkane and we did Br2 in light or heat, and then we got radical bromination, right? Remember that? Initiation, propagation, termination. This is different. This one does not use light or heat, and this is a radical reaction, right? Radical. This is not radical. Non-radical. Okay, so it's a different mechanism, of course. It's going to be like the alkene attacks the Br2 or something like that. Alright? Now, one interesting thing about this new reaction, electrophilic addition of halogens to alkenes, is that it occurs through anti-addition. So there's a little bit of a stereochemistry thing going on, and you can see that if I do cyclohexene and I do Br2, or I'll do Cl2 this time. Anti-addition is going to put one halogen one direction, the other direction, and that's going to be dictated by the mechanism. Okay. All right. So, what is the mechanism? So, I'll show the mechanism on the next sheet, how this actually works. The mechanism of this halogen addition is that we'll just do ethylene as an example, Br2, and you get Br on the one side, Br on the other side. What's the mechanism? Well, what's been the mechanism of these reactions generally so far? The alkenes and nucleophile attacks, and that's exactly what happens. So this kind of attacks here, kicks this kind of off. Now, a funny thing with these halogens is what the intermediate looks like. It actually kind of looks like this. So it's not a normal carbocation. It's like a bromine stabilized carbocation. Kind of looks like an epoxide, right? Remember epoxides with the oxygen? Kind of looks like that. This thing's called a cyclic bromonium. That's the name of it. It's a bromonium, which is kind of like an epoxide, right? And what happens to epoxides? What's the reactivity of epoxides? They get attacked by things. So what's Br minus going to do to this guy? It's going to attack it and kind of open it up like that. So yeah, that's sort of that's the mechanism. That's the mechanism of how halogens add to these things. If we did this for a cyclohexene, it looks exactly the same. We'll do Cl2 this time. What do we get out? Maybe the anti-addition, which will put one chlorine one direction, one chlorine the other direction. Alright, what's the mechanism? This attacks, kicks off a chlorine, alright, kind of like that, I guess. It could be coming towards you, it could be coming away from you. The big thing is that, you know, they are both going the same direction here. And what's the charge? What did we say the charge was on the halogen? It's a weird thing where the halogen is positively charged. So this halogen is positively charged. Then you got the chlorine. Can either attack from the top or the bottom. I'm just going to have it attack the bottom. Cool. There you go. That's how these halogen reactions to alkenes work. Okay. Number 6 is going to be a slightest variation of this. It's the same reaction but trapping with other nucleophiles. Trapping instead of trapping with chloride, what about trapping like with water or something? And that's going to be like Br2 and a water. Okay. Okay, so Br2 and water or something, and the basic result is going to be very similar, but we'll have like a bromine going one way, and then you'll get like a OH, an alcohol, in the other direction. Okay, it's the same exact mechanism. Same exact mechanism. So what's the mechanism? Attack. What's this funny thing called? It looks kind of like an epoxide and it has the same kind of reactivity as an epoxide. It's a transient intermediate, so it doesn't hang around very long. But yeah, it forms. And what do we call it? It's a bromonium, or cyclic bromonium, or bromonia, whatever. Okay, that is electrophilic, right? It gets attacked. So if we have water, and usually the water is in excess, I'll just write excess. So you have a lot of this water around. That's why Br minus doesn't come and attack this, rather water does, oxygen, because you have a lot of it. So water, what's it going to do? It's going to attack. Alright, it's pretty easy, right? And when it attacks from the back. And that's why the Br is one direction, the oxygen's in the other direction. And now, how do we get to the final product? Something takes off that proton, like maybe water, H2O. Something like that. And that is how these form. These are called, there's a name for this product. It's called a bromohydrin. A bromohydrin. A bromohydrin. So you could say trapping with other nucleophiles makes bromohydrin, or it could make a chlorohydrin as well. Alright? Cool. So a little more on the bromohydrin. So bromohydrin, which is just a Br next to an OH, right? Formation is kind of, can be Regio Selective. So what does Regio Selective mean? It's like, kind of like, you know, where does the OH go, where does the Br go? And I'll just show an example of it. So if we have this molecule, and we do Br2 water, well, it's the same exact thing I just showed you. But the question is, where does the Br go and where does the OH go? Like, does the Br, is it mixed, or does one prefer one side, one prefer the other? Well, the answer is that the oxygen goes to the more substituted position. Okay? And there's a very important reason for that. Alright. The oxygen goes to the more substituted, because it's going to be sort of a carbocation-like mechanism. So what's the mechanism? What was the mechanism before? Alkene does what to the Br? Attacks it. We do, that's the way I kind of draw it. I just go from the double bond to the Br2, kick off a Br, electrophilic bromine, right? Who's the nucleophile? Who's the electrophile? The alkene's the nucleophile, the bromine's the electrophile. And what do you make? Ah, this thing. We know about this now. What's it called? What's it called? The bromonium, right? Bromonium. Now, the thing about this bromonium, in most bromoniums, I just didn't really show it before, is it acts like a carbocation. Okay, and it has carbocation character. All right, and it specifically acts like a tertiary carbocation, like a. Let's just draw that in there. It acts like a tertiary carbocation. So its reactivity is like a tertiary carbocation, meaning it kind of is, the structure of it kind of resembles a tertiary carbocation. So it kind of resembles like Br with a plus charge there. So there's a little bit of the bromine is kind of talking to the carbocation. I don't know, I might draw dot dot dot, or just don't even do that. But so there's some overlap between the bromine and, you know, the lone pairs and the carbocation. But the big thing is it acts like a tertiary carbocation. So now what's water going to do to this tertiary carbocation looking thing? It's going to attack it, right? Now you have OH2 plus. How do we form the final product? We lose a proton. Maybe water takes it or something. Water takes the proton. Okay. So this thing's Regio Selective, and the oxygen likes to go to the more substituted side. All right. Cool. And that leads us actually to the next reaction, which remember when we were talking about how, you know, sulfuric acid and water, how that, you know, converts an alkene to an alcohol, and that was the bad way? Well, here's a good way. Here's one good way. This one is going to be Markovnikov. It's going to convert an alkene to a Markovnikov alcohol. It has a long, crazy name, Oxidation, Demercuration. If I was giving it an abbreviation, I might say it's OMDM. And it's going to convert an alkene to an alcohol, kind of like we did before, but that was a bad way. This is going to be a good way. This is a good way. And it's also Markovnikov. What does Markovnikov mean? It means the alcohol is going to go to the more substituted side. Alright, so the basic idea first. And also mercuration. What element do you think is involved there? Mercuration. It's mercury, right? So this is the basic idea. It's got some reagents, so you're going to have to learn these, or, you know, make a good index card. I strongly recommend index cards. In a nutshell, it just converts an alkene to a Markovnikov alcohol, with the alcohol on the more substituted side, right? That's the more substituted, that's the less substituted side. Okay, so the reagents are going to take a little bit of time to study and learn, or just put on your index card. So it's mercury acetate, Hg, OAC2, and water, all in step 1. Mercury acetate, HgOAC2. I'll draw what that means in a second. And the second step is NaBH4, which is weird because you've seen NaBH4, but for other uses. We saw it like for reduction of a ketone or something like that, right? Okay. But this is Markovnikov. Markovnikov alcohol formation, right? Markovnikov. Okay, and we'll also learn the anti-Markovnikov version of this in a bit. So, what if we take this alkene and do the same exact thing? What's the product? Okay, same reagents. Markovnikov alcohol formation of this guy. What's it going to look like? Where's the alcohol go if it's Markovnikov? There's also, you know, an H being added, but we're not drawing that. We just focused on the alcohol. So where's the Markovnikov alcohol of this guy? Well, it's right there. What about the Markovnikov version of this alkene? The carbon skeleton is not going to change, and where's the alcohol going to go? More substitute side, right here. A big important thing here is there's no carbocation rearrangements. So if you did this with sulfuric acid and water, it would definitely make some kind of alkyl shift or something. The molecule would be totally different. So this, why is this a good method? Is because you're eliminating all that carbocation rearrangement stuff. Okay? All right. So how does it do this? What's the mechanism, and how you know, that's what's cool about all these reactions, is their behavior is explained by the mechanism. So let's show how the mechanism works and how it eliminates carbocation rearrangements. Okay, so we'll just say also OMDM, which is oxymercuration, demercuration, is a very gentle transformation. It causes a very gentle transformation of an alkene to a Markovnikov alcohol. It's really cool when you avoid weird rearrangements and stuff. So I'm going to show I'm going to call it the Mark simplified mechanism. So if I ask you about this on the quiz, you can either use the Mark simplified mechanism, or the book often has slightly more complicated mechanisms. I just focus on what I think is the most important part. So let's show just another example. Alright, what's the Markovnikov alcohol of this product? Where's the OH? It's right there. Okay, so for mercury acetate, the structure is O, Hg, O. Okay, so it's mercury, and these things are called acetate groups. You have an acetate group, mercury acetate group, or OH. We call it HgOAC2, right? All right. So, and 2 is NaBH4. All right, we good? So now what's the Mark simplified mechanism of this? Well, what's the general behavior so far in this chapter? What does the alkene do? It attacks stuff, right? So it's going to attack the mercury and kick off an acetate. Alkene attacks mercury, kicks off an acetate. What does that give us? Now this is attached to the mercury, and it's actually going to be attached in a way that kind of looks like the bromonium. Remember bromonium? The bromine thing? And we have a charge on mercury. Okay. Alright, and what did we say, if this is a bromonium, it kind of acts like something. What did it act like? It acted like, acts like, just like a bromonium, it acts like a tertiary carbocation. Okay, it acts like a tertiary carbocation, meaning if I have water around, oh yeah, there's water, don't forget the water, H2O. That's important, the water's important. Now the water, when it sees this thing that acts like a tertiary carbocation, where is the water going to attack? The secondary position or the tertiary position? Because, you know, it acts like a tertiary carbocation. The answer is it attacks the tertiary position. Okay, kind of zoom in there a little bit. So it attacks there. Mercury, the bond goes onto mercury. Alright, so it's two arrows, right? Water attacks the tertiary position, and the bond breaks onto mercury. I should probably draw it larger, but I'll leave it like this. Alright, so arrow 1, arrow 2. So it breaks onto mercury. And then we get this. We got some water attached. Now we have a mercury with an acetate group on it. Am I missing anything? Anything's missing? There's something missing. What's missing? The charge. Okay. Alright, so we get that intermediate. Yeah? Water's attached now with the tertiary position. Now we just lose that proton. Minus H plus. So water or something takes off the proton and you get OH, HG, I'm going to abbreviate that thing X, just because I'm out of space in my paper. Alright, so you can draw it in. It's HGX. So X is the acetate. Is HGX, okay? Sorry, it's a little congested on the page. Alright, that's not stereochemistry, I'm just drawing the bonds. Let's draw that a little nicer. There we go. Alright. And now, how does the mercury go away? That's a great question. Remember the abbreviation is OMDM. Oxymercuration, which adds mercury and oxygen. And then DM is demercuration. OMDM, right? So this is what I call magic. Magic. NaBH4. Magic. Now I don't mean it's really magic, because it's actually not magic at all. It's just not important for this course. If you ask me in office hours, I'll tell you. It's a super cool mechanism of how NaBH4 demercurates it and leaves it with an H. It's not just an SN2. You'd think, oh, this is H minus, right? Like H minus attacks and kicks it off. It's not that. It's more involved. But for now, what do we call it? We call it magic. There's going to be a couple magic steps in this chapter, just things that I don't really want to get into because it's not critical. What's most important about this mechanism is how we get Markovnikov. And why do we get Markovnikov? Because the mercuronium acts like a tertiary carbocation, and the water attacks the more substituted side, and then you lose the proton. And demercuration is actually not that exciting in terms of this mechanism. All right, so that is oxymercuration, demercuration. And I think I pointed this out. OMDM is a great reaction that avoids carbocation rearrangements, which are usually considered a nuisance. It's like you don't want those to happen. Let's just show another example of that. If I have it's a benzene, methyl, alkene, HgOAC2. Remember, you need water in the first step. NaBH4. What does it do? What is the reaction? What does OMDM do? It makes what? Don't forget the benzene. It makes Markovnikov alcohols, right? So it makes this. Okay. But what was the bad way to do this reaction? The same exact reaction. You could just use H2SO4 and H2O. That was the bad way. Remember the bad way? And you would probably get more something like that, because it would alkene would attack the acid, you do a hydride shift, and then you get this. One more little thing, we have benzene here, right? Are these like really like the same kind of double bonds as this double bond? The answer is no. This is totally different. Benzene has its own little world of reactivity, and it's actually a later chapter. So you'll learn about it in organic too. Chapter 16, 15 and 16, I think, are the chapters, the alkene or the benzene chapters. All right. Okay, so we did. What was the last reaction we just did? We did. It was at an abbreviation. It was OMDM, right? Which made what kind of alcohol? Markovnikov or anti-Markovnikov? So it made Markovnikov, right? So now we're going to do the anti-Markovnikov version. It's called Hydroboration. It's another weird, crazy word. Oxidation. Hydroboration oxidation. What would be a good abbreviation of that? HBOX. Hydroboration oxidation. What this does is it converts an alkene, not into Markovnikov alcohol, but into an anti-Markovnikov alcohol. Anti-Markovnikov alcohol. Anti-Markovnikov alcohol. Alright? So it's going to be a totally different mechanism, but it's a really useful transformation that we can use in organic synthesis. Alright, so overall, what do I mean by anti-Markovnikov alcohol? And what's the general reaction in the reagents and all that stuff? So, what is the anti-Markovnikov alcohol of this alkene? Is it more substituted or less substituted? It's less substituted. So the alcohol goes on the less substituted side. Then the first question, or what are the reagents to cause this? This is another two-step process where the first step is BH3, borane. BH3 is borane. And the second step is H2O2 NaOH. BH3, H2O2, what's that? That's hydrogen peroxide, which is, it's like HOOH, right? And then we use sodium hydroxide in the mix, alright? So if we have, let's just do a couple more examples, and then I'll show the mechanism. Okay, this also avoids all the carbocation rearrangement business. Okay, what's the anti-Markovnikov alcohol of this? Where's the OH go? On the less substituted position. What about on this alkene? Where does the alcohol go? Actually, what we're going to do, maybe I'll just convert this into a little synthesis problem before we even do the mechanism, but we can still use it as a synthesis reagent, right? Okay, we're learning new reactions, right? And what can we do with new reactions when we learn about them? Use them. So let's just do this retrosynthetically. Look at this, look at that. Where's our squiggly line? Right there. And how do you make an alcohol with a CC bond like that? Maybe make it from a what? What functional group? And what reagents? What functional group and what reagents? Maybe from a Chapter 8. What is it? Looks like that, but but of course it's probably a Grignard, right? And we know Grignards don't add to alcohols, they add to ketones and aldehydes and epoxides. Now we know about epoxides, right? So maybe the benzene attacks the ketone. Alright. And what is it? 1 and 2? Water is step 2. So maybe it's benzene, magnesium bromide. Foul magnesium bromide. Okay. Oh, but we're still not done then. How do we go from the alkene to the ketone? Well, we know about, what do we learn about? Anti-Markovnikov alcohol formation. So we can probably convert this to an anti-Markovnikov alcohol, but that's not what this is. It's a ketone. So one extra step, right? First, let's do this step. This one you know from chapter 8. Oxidation with maybe PCC, right? 1 bond oxygen to 2 bonds oxygen. And now this is the OMDM reaction. OMDM. No, OMDM. HPOX. So it's what do we say it was? It's BH3, H2O2, NaOH. BH3, H2O2, NaOH are the conditions for the hydroboration oxidation, and it's going to involve boron BH3. Okay. All right. Cool. So we had a couple examples here, including a little mini synthesis, a reasonable little mini synthesis. So these are all Markovnikov or anti-Markovnikov? Anti-Markovnikov. Markovnikov. Alright. So now, just like before, we're going to do a Mark simplified mechanism of the of the hydroboration oxidation, HPOX. Hydroboration oxidation. Let's see the Mark simplified mechanism of this one. Alright, so we'll show the mechanism of this. And I'm also going to call this one a Mark simplified mechanism. So there's a little bit more to this mechanism, and the book goes into detail. We're going to skip a couple of the details just to make this as simple as possible. My main goal here is to explain why it's anti-Markovnikov, and we do that pretty effectively. Alright, so we'll do methyl cyclohexene. What's the anti-Markovnikov alcohol of this alkene? The hydroxy group will be on the least substituted side. There is actually a little bit of a stereochemical consequence of this, and I'm going to show it now. If depending on the substrate, we wouldn't need to draw the stereochemistry. It's just because it's a cyclic molecule. We definitely see that the H and the OH are same stereochemistry. So there's also the enantiomer of this that's formed, which is H OH. All right, but that's not that critical. And for the sake of the mechanism, we're just going to focus on this one enantiomer, but they both actually do form. All right. So what is the reagents? It's BH3, H2O2, and NaOH, right? Okay. So what happens is borane, BH3, will line up and kind of add to the alkene. So what I'm going to do is draw H, B, H, H. Okay? So it lines up like that. And we're going to draw little arrows, or dots. Dot, 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 dot. Okay? So that's where the electron flow is going to happen between The 2 carbons and the H and the B. So it's just 2 arrows. This is like this and that. It just adds. You can do the arrows one way, you can do the arrows the other way, it doesn't matter. The big thing is that carbon gets a hydrogen and boron gets a hydrogen. Sorry, boron gets bound to carbon. Okay? And what the relative stereochemistry are going to be the same. So if hydrogen is kind of like going away, then the boron's also going to be going away. We'll see the boron gets converted to the hydroxy group through another step. But the relative stereochemistry is the same. Alright? So the 2 things that are being added, in this case the hydrogen and the boron, are going to have the same stereochemistry. Alright, so what do we get? What does it look like? So I'm going to just focus on this stereochemistry here. So we'll start the methyl going kind of towards us, and then it's like dash 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 H dash 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 BH2. Alright? So I could make this wedged out actually too, but that's whatever. Alright, so hydrogen and boron both get added. Now there are subsequent steps of how the boron gets converted to the hydroxy group, and that's how involving H2O2 and NaOH. This is another one where, kind of due to the lack of time, I'm just going to write magic. It's not that big of a deal. We can talk about it in office hours, or you can look in the book. The book does go through this mechanism. The basic gist of it is that the base takes this proton, you get OOH, it's a peroxide anion, and then this reacts with boron, then does a couple other steps. But I'm happy to just call this magic from boron to the alcohol. Okay, so net effect though is boron gets converted to the alcohol, and that's your anti-Markovnikov alcohol formation. In this case it's a mixture of enantiomers, but you don't always have a stereochemical consequence. That's the basic mechanism. Alright, so why is it anti-Markovnikov? Why is this whole thing anti-Markovnikov? What causes it to be anti-Markovnikov? If you look at this, does the boron want to be really close? You know, the boron BH bond can either be this orientation, or it could be like boron BH2 on top, hydrogen on the bottom. So which is more sterically favored? If the boron is away from stuff like the methyl group, right? That's why it's anti-Markovnikov, because the boron can be away from all the action, right? If it was flipped over, if this thing was flipped over and it was like BH2H, then the BH2 would be talking to the CH3 and it wouldn't be very happy, right? That is why this reaction is anti-Markovnikov. Okay? Okay, but I'll just say in the book is a more complete mechanism. You don't need to know the complete mechanism for this course. All right. And why was it anti-Markovnikov? The boron wants to be away from the steric clashing of the methyl group. Boron avoids the congestion of the methyl group, and therefore the boron wants to be kind of like poking down in this example. Okay, so I'll just show that. In a nutshell, we were showing this. as our kind of transition state, or yeah, those two things coming together. This is good. The alternate method, or alternate way, would be BH2 kind of that way, and that would be bad. So that makes sense, and that explains why hydroboration oxidation is an anti-Markovnikov method. And just an example, kind of comparing OMDM versus HBOX. The OMDM was Markovnikov. The hydroboration oxidation was anti-Markovnikov. And let's just draw an example. Where we do one or the other. Okay, top one will be oxymercuration. It's HgOAc2 and water. NaBH4. And the bottom will be hydroboration oxidation, HBOX, the boron one. BH3, NaOH, H2O2. Alright. So what's the, I'm going to draw the top one kind of right there. What's the top product look like? That's the carbon skeleton, and where do the alcohols go? If it's this one, the mercury one is Markovnikov. Where do the alcohols go on the more substitute sides? OH and OH. All right, more substitute sides of the alkenes. Whereas hydroboration oxidation, the boron one, where do the alcohols go? There's the carbon skeleton. So, carbon skeleton's good, yeah. Hydroboration oxidation, least substituted, and least substituted. See what we did? That's a good comparison of the two methods. The mercury one, which is Markovnikov, the boron one, which is anti-Markovnikov. Let's just do a little mini synthesis problem that, just to reinforce this a little bit. This is easy. What I'm trying to do is kind of emphasize the coolness of retrosynthesis. The coolness of retrosynthesis, right? So we know where it's coming from, but we got to figure out, you know, the sequence of reactions to get to the product. And start with a squiggly line, right? You got to know your reactions in the forward direction and the backward direction. You need to know the reagents, and it looks like we're adding a 3-carbon piece, maybe to a ketone to make a tertiary alcohol. Right? 3-carbon piece, right? It's that. 3-carbon piece, right? Yeah. So maybe propyl vineyard. Alright, now it's like we're going kind of from a alkene to what looks like a Markovnikov ketone, but you don't know how to make a Markovnikov ketone. You know how to make a Markovnikov alcohol though, right? How do you make a Markovnikov alcohol from an alkene? Markovnikov alcohol, is that the hydroboration or the oxymercuration? It's the oxymercuration, OMDM. You can write down the reagents. It's the mercury acetate, water, NaBH4. Then how do we go from a secondary alcohol to a ketone? 3 letters. What do you think? 3 letters. Oxidation. PCC. Alright. Just another example of a little mini synthesis. That's pretty cool. Okay, this topic we're going to skip. I'm just going to mention it, and you can read about it in the book if you want. It's not a critical one. It's number 9. Is another reaction of alkenes. Carbenes to make cyclopropanes. The gist, I'll just show the gist of it, okay, is that if you have an alkene and you can react it with certain things, you can make cyclopropanes, which are really weird molecules, right, because they're very strained, right? Cyclopropanes are really strained. I'll show the basic gist. This won't be on the quiz or anything. Let's draw 2 R groups here. Alright. It's actually a really simple reaction, but there's a little bit to it, and I don't want to go into detail. But 2 electrons go one way, 2 electrons go the other way, and you make these things. So if you want to read more about this, you can read about it in the book, but I'm going to otherwise skip it, kind of due to lack of time. Alright, carbenes to make cyclopropanes. This funny thing is called a carbene. I'll just mention what that. It's a carbon with 2 R groups and a lone pair, no charge. It's a weird reactive intermediate type thing. And anyway, they react with alkenes to make cyclopropanes. That's all I'll say about that. Read about it in the book if you're interested, or we can talk about it in office hours. Alright, so number 10 is a reaction that you guys already learned about, which is making epoxides via a special reagent. Remember the special reagent? 5 letters? What are the 5 letters? It was MCPBA. So the book doesn't talk about that in chapter 9, but we talked about it in chapter 9. So you already know about this. I'm just going to show it again, but I'm not going to review all the mechanism. Right. So if you want to make an epoxide, which are really cool because there's a bunch of reactions you can do to them. Reactions, right? Openings and everything. You can use MCPBA. MCPBA, which was metachloro peroxy benzoic acid, and this was all chapter 9, so I'm going to refer you to chapter 9. You do need to know the mechanism. It was that cool mechanism where you have to redraw this oriented with the alkene, and then it's concerted, a couple steps, right? So that's all I'm going to say about that, because we already know about it. I'm not going to review the mechanism. But you should also review from chapter 9, all the different kind of opening reactions of epoxides. That stuff's really cool, and probably going to see that on the final exam. Alright, so that's number 10. Another reaction, epoxides being made from MCPBA. Alright, so another reaction. A bunch of them, huh? So we learned about making alcohols from alkenes. What about making two alcohols? So this one's called dihydroxylation. Dihydroxylation. And it uses another weird metal, another heavy metal oxidizing agent called OSO4. What's the metal OS? It's on your periodic table. It's osmium. Osmium tetroxide. Okay. Straightforward reaction. I'll show the mechanism and an example. Alright, so alkene, and what it does is it attaches two hydroxy groups, OH. The stereochemistry is the same, so this is also called a syn addition. The boron thing did this too, hydroboration oxidation, where the two things get added opposite. What was it called if it went backward? Like bromine, remember Br2? That was backward. That was called an anti-addition. This is called a syn addition. So syn additions and anti-additions. So it's OSO4, osmium tetroxide, H2S, some kind of sulfur salt. Very simple mechanism. I'm also giving a slightly simplified mechanism of this. Alright, so let's draw that cyclohexene. The way to do this is you draw osmium, double bond to O, double bond to O, double bond to O, double bond to O. You have to draw it kind of that direction, that orientation, right? And now we're going to draw a dot, 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 and a dot, 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 dot. So the syn additions always have this kind of concerted addition where you have a bunch of arrows, and this is exactly the same type of thing. So double bond goes there, pair of electrons go into osmium, double bond goes there. So it's just three arrows. You can go one way, you can go the other way. The direction doesn't matter. Bottom line is the osmium gets reduced because you're adding a pair of electrons onto osmium. And what does this give you? It doesn't give you the product, it just added osmium to your molecule, right? That does give you the syn addition. Osmium, and then so the stereochemistry is all set up. So the last step I kind of abbreviate, and I'll just tell you the basic gist of it. Alright. So the sulfur thing you got, H2S. Well, sulfur loves osmium. Sulfur has an affinity for osmium. So what do you think it's going to do? It's going to attack it. And it just kind of breaks these off. So it's probably a multi-step process where, you know, it attacks, kicks one off, maybe attacks again, kicks the other off, and then the oxygens get their protons from water or something. In that result, those you go from the alkene to two hydroxys. So a lot of times students ask, well, where do the protons come from? Well, the protons are coming from solvent or maybe from H2S. This is our abbreviated mechanism. You know, if I ask you about this on the quiz, I would probably just say, how do you get from here to here? And that's really easy. It's just the concerted addition of OSO4 with the alkene. Okay? Alright. I'll also show an example, another example of this. Now here there's no stereochemistry or anything, but it's just the same exact thing. 1 OSO4, 2 H2S. Alright, so alkene kind of react, I'm not showing the mechanism, I'm just showing the reaction. The alkene reacts with OSO4, and then the H2S kind of kicks off the osmium, and then you get the product. Okay, so another reaction. We have just a couple more. I think 2 more. There's this one and 1 more. This one's called ozonolysis. Ozonolysis of alkenes. Ozonolysis. What do you think ozonolysis uses as a reagent? Maybe ozone, and it's just ozone is O3, right? O. It's kind of a weird molecule, plus charge, minus charge, O3. What does lysis mean? It means cleavage. So this is a cleavage of alkenes. A rare example where we're cleaving bonds. The basic idea of it is, so it's O3. You have a second reagent workup step, zinc, HOAC, which is acetic acid, or that. And what happens is you just cleave the bond. It cleaves it. Just snips the bond in 2, and so you get cleavage of the CC bond, and that gives you 2 carbonyls. That becomes an aldehyde, and that becomes a ketone. So it just snips the bond in 2. So I always just give a kind of a simplified mechanism for this one too. Just shows the very basic idea of the mechanism. All right, how does this work? How do we get the cleavage reaction to go with ozone? Alright, so what we're going to show is ozone, which is O, O, O. Same kind of thing like before, where it just lines up, kind of like osmium did this too. So dot 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 dot. Alright, so we got some, it just lines up. Now start with the negative charge, the O minus with the negative charge. Make a bond, and just kind of 3 arrows in a circle. So just kind of snaps everything together. Okay? What does that give you? It doesn't give you the product. What does it give you? What does the arrows do? It just simply gives you oxygen, oxygen, oxygen. Right? It just snapped ozone onto the molecule. This has a name. It's called a primary ozonide. A primary ozonide. Okay? That's easy. I would argue that's actually a pretty easy thing that just happened. Then something kind of weird happens, which is not totally easy, but the structure is pretty easy, where one oxygen, one of the 3, I think it's one of the oxygens, kind of sneaks in between the 2 carbons. What's that look like now? So it looks a little weird. Oxygen, oxygen. See what I did? I just took one of the oxygens and snuck it in between the CC bond, and now it's still a 5-member ring. 5-member ring, 5-member ring. What do you think this thing's called? If this is primary ozonide, this is called a secondary ozonide. secondary ozonide. And then this is magic. This is actually less magic than the other magic steps because it is, you will learn this part in organic too, kind of how these things kind of cleave to make carbonyls. So, but for you guys, you know, what would I focus on? How to make the primary ozonide, and then of course just the structure of the secondary ozonide. I'm not showing you a mechanism here. The mechanism is kind of weird. The book does the mechanism. But at least the structure of the primary ozonide, the structure of the secondary ozonide, and you know, that's sufficient for this reaction. Okay? Just 2 more examples of the reaction. O3, zinc, HOAC is acetic acid. What's the product of this? Just draw the product. What's the product? Maybe draw a squiggly line to show, oh, we're cleaving the bond, right? And if the bond goes away, what do you got? It's still attached. So you still have this carbons, right? And now you got a ketone and a what? What's that called? Aldehyde, right? So it just cleaves the double bond and gives you a ketone and an aldehyde. Okay? One more. What about this one? I'm just going to say quotes to suggest the same reagent. What is this going to give you? What's going to happen? It's going to cleave this, and it's going to cleave that, and give you what? What are the products? What's a 1-carbon carbonyl? Like a 1-carbon aldehyde. 1-carbon aldehyde is called formaldehyde. Oops. And then you got, on the other side, you got a ketone, right? Ketone there, ketone there. So is it ketone there, ketone there. So ketone there, right? And then this thing is a 1-carbon carbon, 2-carbon carbonyl. Looks like that. Alright, so it basically gave you 3 products. It gave you, you cleave both double bonds, you get a formaldehyde, a diketone, and a 2-carbon aldehyde, acetaldehyde. All right. Okay, so we're kind of at the end of the lecture. We have one last reaction. I'm going to show it. This may be an extra credit mechanism, so it's not that hard, but I do want to show it, and possibly extra credit mechanism. I need to show it. It's pretty cool, and you know, we're just a little low on time. And you should know at least the reagents and the product of this reaction. And it fits into the theme of the rest of the reactions that you learned about. All right. So, what else about this? Oh yeah, and I'm also at the very end, I'm going to add I'm going to have a little summary. I'm going to draw a summary of all the reactions that we just kind of blasted through. Summary scheme. So I'm going to show that also. Alright, so let's do this last reaction now. Alright. So now we're on to number 13, the last reaction from Organic 1. Number 13. Alright. So this one's not that crazy, but it's kind of fun, I guess. This is radical addition, It's another reaction. RXN. Reaction. Radical addition of HBr. So at the very beginning of this chapter we talked about how HBr added to alkenes. Remember that? Very beginning. For almost the first reaction you learned about. And we said it was Markovnikov, right? This is Anti-Markovnikov. And it's going to be a slightly different mechanism, and it might be a cool little extra credit-ish type mechanism. Alright? So recall that, from the very beginning of this chapter, what did we learn? What did we learn? We learned that HBr, would react and you'd get the Br there. Was that Markovnikov or anti-Markovnikov? It was, right, the carbocation. There's the H, right? Yeah. So it was a carbocation type mechanism, right? Br minus, alright. Okay, so what we're going to show now is an alternate way of doing this. I even mentioned this earlier, but where the bromine actually goes anti-Markovnikov. Anti-Markovnikov. And it was HBr plus something else. Do you remember what the other thing was that we have to add for the anti-Markovnikov? It was something called peroxides. Peroxides. HBr peroxides, and the peroxide specifically that we draw is tert-butyl peroxide. So it's tert-butyl, oxygen, oxygen, tert-butyl. Tert-butyl, oxygen, oxygen, tert-butyl. Alright, and it's a really cool mechanism that causes it to be anti-Markovnikov. So let's show that mechanism now. Okay, so what's the mechanism? It's kind of cool because this is almost related to the very first mechanism you guys learned, because it's actually a radical mechanism, but it's a little different. So it's actually a multi-step mechanism. First step is kind of like an initiation step. So the peroxide, maybe with a little bit of heat, breaks the bond. Fishhook, fishhook. So there's a radical mechanism. Remember radicals and the little fishhooks? Okay, so you get a pair of these oxygen-centered radicals. Okay, that's easy. Mechanism step 2. Now that you got an oxygen radical, it reacts with HBr. So oxygen loves protons and hydrogen atoms. So the oxygen sees the hydrogen atom and it takes it. It just rips it off. So 3 fishhooks. Fishhook, fishhook, fishhook. And what does that make? What kind of functional group does that create? An alcohol. And a what radical? A Br radical. Okay? So what this basically did was we broke the peroxide up, made a couple of tert-butoxy radicals. One of them grabbed HBr proton. Not really proton, it's a hydrogen atom. And made a Br dot. Alright, so what is step 3? So now now the actual fun part happens. So now your radical sees the alkene So an interesting tidbit about radicals is radicals actually can add to alkenes through a new mechanism that you have not seen. It's really easy though. Let's redraw it. Br dot. So the Br dots use the alkene. So it's going to do 3 fishhooks also. So fishhook, 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 fishhook. And what happens to the Br? It just kind of attaches. The Br attaches to the bottom carbon. And what kind of radical does it make on the carbon above? What kind of radical is that? Is it a happy radical or an unhappy radical? It's tertiary radical. And we know tertiary radicals are happy or not. They're very happy, right? Remember how radical stability kind of paralleled carbocation stability? Very first thing you learned about radicals, you know. So yeah, so that's you know, given the choice, forming a tertiary radical is kind of favored, right? If the bromine did the opposite and attacked the other carbon, because it could have, this bromine dot could have attacked that carbon and then forced the radical onto the secondary position, right? So this could have attacked there and made a secondary radical, but a secondary radical is not very stable, right? That is why this is anti-Markovnikov. That's why the Br goes where it goes. Okay? And there's one last step. What's the last step? The last step is step 4. What's the final product? You know, you have, what's that there? It's a hydrogen, right? You need to get an H at the tertiary position. So what's the last step? Mechanism step 4. Now the radical just rips off that hydrogen and creates a new Br dot. And what does that make? The final product. Okay, cool. So that's the overall mechanism of this HBr peroxide Anti-Markovnikov Hydroboration, which just means we're adding an H and a Br, right? Kind of like an initiation type step. O dot takes a hydrogen atom from HBr, makes a Br dot. Then the Br dot adds to the alkene to make a tertiary carbon radical. Tertiary carbon radical grabs a hydrogen, creates a new Br dot. And so, of course, yeah, we make a new Br dot, and that's kind of the propagation step, right? So you are kind of creating an initial Br dot, and then we consume a Br dot, create a new Br dot. So it kind of goes in a circle. These are like a propagation sequence. There's probably termination also, but we're not going to really care about that. There's definitely a termination step. But these are like propagation 1, propagation 2, propagation 1, propagation 2. Okay? Okay, so mostly done with this reaction. Just want to show a couple examples of it real quick. Just simply. So this is the peroxide one or the non-peroxide one? This is just the normal carbocation Markovnikov one. Remember, you might get a carbocation rearrangement or something, right? So C rearrangement. You could do that mechanism, right? You should be able to do this mechanism. Alkene attacks the proton, makes a carbocation, do a hydride shift, hydride shift from the CH and then carbocation there. What if we do the anti-Markovnikov version? What's the anti-Markovnikov version of this? HBr peroxide. Well, this avoids all the carbocation business because it's a radical mechanism, so it just makes that. Just makes the anti-Markovnikov bromide. Alright? Cool. Alright, so that is the end of the course material. A lot of stuff, and I know this last chapter is a little overwhelming, so you have to it's going to take a little bit of time to review it, but you know, if this is being an open note course with the online learning, it really makes this a little bit more manageable, I think. What I'm just going to do is, just as a kind of a review activity, I'm just going to draw all the products just that you can make with an alkene, given like a simple alkene like that. And then you can kind of start thinking about, you know, how you might review the reagents. But since it's open note, memorizing the reagents is not that crucial. Remember, in the normal course, you actually have to memorize these, and that makes it kind of difficult, right? But anyway, let's just it's still useful for you to have an idea what the reagents are, right? And so, certainly if you're going on with chemistry, or if you have to take MCATs and stuff, yeah, you're going to have to memorize every one of these things, because you'll have to know them all, right? Alright, the first reaction we did was just loss of the alkene, right? What was that? That was catalytic hydrogenation, so it's just H2 palladium. Okay? Then we learned about Markovnikov hydrobromination. Markovnikov hydrobromination. What was that? It's Markovnikov, so it's, you're adding HBr, but it's Markovnikov. It's not anti-Markovnikov. So that was just HBr. Okay. What was the reagent or whatever to add two BRs? What do you think? What was it? It was BR2. BR2. That's pretty easy. And remember also, you also were able to add a BR and an OH. Remember that? It's kind of very similar to the BR2 reaction. And the mechanism is very similar. Because remember, I went through a bromonium, the weird 3-member ring with a bromine. This is BR2 water. Okay. Alright, what else did we do? We learned how to go to a Markovnikov alcohol. Oops. Markovnikov alcohol. How do you do that? Markovnikov alcohol was oxymercuration, demercuration. OMDM. Remember? Two reagents for OMDM. What were they? HGOAC 2 and water, and NaBH4. Okay. And you could also make the anti-Markovnikov. Whoa, my bad. My bad. Anti-Markovnikov alcohol. What was that one? That was not the mercury one, it was the boron one, HBOX. HBOX. Alright, HBOX. What were the reagents for HBOX? Boron something, right? It was a BH3, NaOH, H2O2. H2O2, okay? Alright. What else could we do? We could also install 2 hydroxy groups. So I'm kind of ignoring stereochemistry right now. I'm just for the sake of reviewing these reactions, because it is a syn addition, and the OHs would be on the same side, but that's kind of irrelevant here. What was that one? It was the OSO4 one. OSO4, and then some kind of sulfur thing like H2S. Right? Remember that? Dihydroxylation. Okay. This one was not... We didn't really talk about it. I'm just going to draw it though anyway. If you want to learn about it in the book, it's the cyclopropanation, making cyclopropanes. Not really something you'll see in my course again, but it is a really cool thing you can do to alkenes. Cyclopropanation. Anything else? Did I draw anything? Miss anything? What about epoxides? How do you make an epoxide? 5 letters. Something, 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 something. MCPBA. It was that weird concerted addition reaction, alright? Anything else? Did I miss anything? Oh yeah, and of course from epoxides you can do Grignard opening, MGBR, all that kind of stuff. Remember that from chapter 9? Right, the Grignard attacks from the least inner side and opens up the epoxide. Okay, anything else? There's 2 more. One is remember the kind of last reaction we just talked about. The alternate to the Markovnikov HBr. The alternate to the Markovnikov HBr is the Anti-Markovnikov HBr, right? With peroxides. These 2, I'm going to skip the reagents just because I don't have space anymore. It's Br there, right? You can draw them large on a piece of paper. This would be a great thing to draw for your own review and throw in the reagents and everything. But that one, the Anti-Markovnikov HBr is HBr peroxides, right? It's the radical reaction. Okay. The other one is the Ozonolysis, which is that cleaves the double bond. It cleaves it, right? What's the reagents? It's O3, and then kind of like, I think zinc acid, zinc acetic acid. O3, zinc acetic acid. Okay, cool. So I'm going to have something like this on the website also. There's kind of 2 versions of this sort of scheme. One where you, like for practice and remembering these. One is you fill in the reagents, and I have a version of that, like that. And the other is I give you the reagents and you fill in the products. So with that, you can kind of use these, because you were going to be using these and other reactions all the way to the end of organic 2. So you kind of got to know this stuff. So there's a little bit of studying, just like a foreign language or something, right? All right, that is it for organic 1. And yeah, so there's going to be some study materials on the iLearn site that you can use, and if you have other questions, you can come to my office hours. All right, good luck.